So, good evening, everyone. I'm Calvin Joseph, and today I'm going to conduct the week 9 problem solving and calculating session for the course State Space Approach to Control System Analysis and Design. It's from the Professor A.P. Tiwari of IIT Nagpur. Okay, so today we will be considering three types of control. Okay, and like to emphasize that this is based on discrete data sample systems. Okay, so the first one is the multi-rate output controller, MROC. Next, we consider what is fast output sampling, FOS, which is a subsection of seems like a specific condition in which fast output sampling is a subset of analysis. Then next we consider periodic output feedback, POF control. Okay, so start with this session. So now we will be going towards what is known as digital control. We consider three types of digital control. It's so as in this last week. This is for week 9. And till now, we were considering continuous time systems. Okay, so these systems will have this term 1 by s. Like 1 by s is like basically they have what is known as equilibrium. Now we go to the system, basically the time systems, and they will have what is known as a z inverse or a delay. So a continuous time system is represented by differential equations. And a discrete time system is represented using difference equations. So we know what is the condition for stability. For a continuous time system, the poles should be in the left half of S plane. So this is your S plane, this is your sigma, this is your j omega. So your poles can lie over here. As long as your poles lie here, your system is stable. Next is discrete time system, DT systems. Here, poles should lie within the unit circle. So basically we have this, right? This is a unit circle, this is your Z plane. This is your 1, 0, 0, 1, 0, -1, -1, 0. So this is the real part, this is the imaginary part. So your poles should lie within this unit circle. If your poles lie within that unit circle, then your system is stable. So pole locations, they differ. And why you must understand this? Because you will do, when you do pole placement, the criteria for selection of the pole locations will be different. Okay, so this is what I wanted to highlight over here. Now you will go to Sir's lecture notes and we will try to understand what is multi-rate output controller, what is fast output sampling, what is periodic output feedback control. Okay. So we have a system. Okay, we will consider the linear time invariant system. It has an input U, it has an output Y. Okay, so now what happens in discrete time systems? You see over here. So this is our linear time invariant system, and it can be represented like this. This is the system represented in the form of a B, C matrices. Okay. Now we will consider what is sample data control system, what is discrete time control systems. Right. So what happens is the system is the inputs are updated only at discrete instance of time. That is, your input is not continuous. It is changing. It means one value, then after some time it goes to another value. It remains there, then it goes to another value. So that so this occurs in these systems, as well as the outputs are observed only at discrete instance of time. That is, we view the output only at certain instance of time, not continuous. Because that's why they are discrete or sample data systems, right? So what they use is a switched. They use a switch is used over here. Suppose this UT, this is U of KT in this system, Y of T, T is Y of KT. So you must remember your system will still remain a continuous time system, but your input and your output are different. Okay, they are different. So let me draw that will make it more understandable. So this is your U of T, this is your Y of T. Okay. Now, so what does this mean? Your input can be changing like this. Your output would be changing something like this. This is your input and your output. Now let us consider a case for a sample data system. So you still have a linear time invariant system. Okay. But the difference is over here, you have U of KT, you have a switch, and this is your U of T. Similarly, you have a switch, this is your Y of T, and this is your Y of KT. Right? So if you will observe, okay, so it is also sampled at a rate of T. Rate of T. So your input in this case will be like this, something like this. Okay, where this is your time T, which it will change. Your output may be varying like this, all right? But you will be taking the sample only over here, over here, over here. So this time is your T. So basically, you are doing what is known as uniform sampling. So at a fixed rate, you are observing the output. The fixed rate, you are seeing what is the output looking like, how does it look like, what are the samples. So to do all this, you would require what is known as an ADC. ADC. That is an analog to digital converter. This would be required in your practical system. Because what you must understand that the real world is analog. Okay, this world that you see, it is analog, it continuously varies, there changes, there continuous variations. But you want to control that analog system. So to control that analog system, you will have to take certain samples. Okay, so let us consider one example. Let us say I have a series RLC. Okay, this is series RLC. This is your resistance R. This is your inductance L. This is your capacitance C. Okay, and this is your input. Okay, and this is your output, and this is your current, which is your inductor current. Now, this is your what we do is, and this is your ground. Okay, this is your ground. So this voltage, we will take it to an ADC. So suppose this voltage is 1 volt, your ADC will convert it into some number depending on the bits of the ADC. Okay, let us say it will convert into some number, converts into a digital number. Let us say it converts to 1027. Okay, 1 word corresponds to a digital number 1027. So this is a digital thing, and it will be in terms of bits, number of bits, depends on the bits of the ADC. Usually we have what is an 8-bit ADC, 10-bit ADC, 12-bit ADC. Okay, depending on the bit size of the ADC, you will get more minute and correct values. Okay, so what we are doing is we are seeing the output voltage. The output voltage is changing continuously. Your capacitor voltage probably, let us say your capacitor voltage was changing like this. Okay, but you're taking samples at fixed point. You take a sample here, 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 you take a sample here. Okay, and those sample values will look like this. It will look like this for some time. If you hold that value, then it will hold this value, and then if you hold this value, it will go lower value. Then if you hold that value, it will lower value. Hold this value, it will hold this value. Okay, so this is your continuous time system. This is your discrete time version of this same thing, the same value. All right. So let us see what Sir has shown. So now they are saying that we have the system. It has certain equations. And what are the equations for this system? How do we get it? Okay, so we have a continuous time system. My original system is a continuous time system. X dot is equal to AX plus BU. And this is how by the state transition matrix formula which I taught earlier, this is how the state changes with respect to time. This is how it changes with respect to time. What they do is they will set some conditions. Time is kt plus t and initial time is kt. So they're considering one sampling period of capital T, which is fixed for both the input as well as for the output. So they want to see how my system behaves, how my system's response varies. Okay. So also they treat the input as the output of a zero edge. That is, their input is constant. It does not vary. This is the assumption which is there. And if this in certain systems is true, in certain systems it is not true. But if your sampling period is very small, then this assumption can be considered to be valid. Okay, so then they find the expression of x k plus 1 t. It is finally given by this expression. Okay, so let us say I have a system which is given by x dot of t is a into x of t plus b into u of t. This is a continuous time system. What Sir has derived is, he has found out the value of x of k plus 1 t is equal to some phi into x of kt plus some gamma into u of kt. Okay, this for the discrete time system where input is from a zero order whole. That means my input will not change like this. The input will change like this, like this, like this, like this. So this is my input. My input is no longer continuous. It is no longer continuous. It is discrete. So for the time period t, this time period t, we say that the input is discrete. It is fixed. Okay, it is coming from a zero order pole. Okay, that is shown over here. And what are this expression of phi of t and gamma? Okay, so phi of t, this phi of t is equal to e to power at, and this gamma is integration of 0 to t e to power a t b. Actually, it was e to power 8 tau, if I'm not mistaken. Okay, e to power 8 tau b into d tau. A tau b into d tau. Okay, so this is the expression for gamma which has to be evaluated, and then we can get what is out. Right? So once we get this information, in this we are assuming that the samples are taken of the input as well as of the output at the same rate. Both the samples are equal. And so what is the output y of kt is equal to c into x of kt. Okay, so this study of this set of systems is a very evolving and is a very dynamic subject, and which is very relevant to this day and age where many of the controllers are becoming digital, and problems which are associated with digital control are there, like there's certain additional delay, there's quantization, etc. But there are certain various flexibilities which digital control provides, right? So these things, it's a very important subject. Okay, so what have we assumed over here? So let us try some sum to get better understanding. What we will consider is a uniform sampling of input and output at a rate of t. Okay, at some rate of t. Let us say A is -1, 0, 1, 2, and B is 0, 1. Assume this is my A and B matrix. So how do I find phi? How do I find this gamma? Okay, let us see how do we do that. So this is my A matrix, right? So my phi of t is equal to e to the power A into capital T. Okay. Then let me make it simple. My phi of small t is equal to e to the power A into small t. This is basically the state transition matrix. So how do you find the state transition matrix? Which Sir had shown earlier, the easiest way, which I prefer, which is easy for me to remember, is using the Laplace transform. So what we do, we first find S of I minus A. That is S 0, 0, S, okay, minus of A, -1, 0, 1, 2. So this comes out to be S plus 1, 0, -1, S minus 2. Okay. Now I have to find the inverse of this. So Si minus A inverse. What happens? This gets interchanged. S plus 2, S plus 1. 0 remains as it is, minus of 0, and minus of -1 is 1 upon that product. Okay, this should be -2. Okay, it is S minus 2. So this is S minus 2 into S plus 1. Okay. So this actually is S minus 2, 0, 1, S plus 1. Divided by this S minus 2 into S plus 1. So this is common. So we will take it inside. So my system becomes equal to 1 upon S plus 1, 0, 1 upon S minus 2 into S plus 1 upon 1 upon S minus 2. This is my system. So now, this 1 upon S minus 2 into S plus 1, let us consider this. Let us tackle this. What is this? 1 upon S minus 2 into S plus 1. This is some A upon S minus 2 plus B upon S plus 1. So we get 1 is equal to A into S plus 1 plus B into S minus 2. So we get 1 is equal to A plus B into S plus A minus 2B. So we get A plus B equal to 0 and A is equal to 2. We get A minus 2B is equal to 1. Okay, so what we can write, A minus 2 of minus A is equal to 1. So we get 3A is equal to 1, or A equal to 1 by 3 and B equal to -1 by 3. So we can write 1 upon S minus 2 into S plus 1 is equal to 1 by 3 into S minus 2 minus 1 by 3 into S plus 1. Okay, so this has been written. So now we'll substitute here. So my phi of S, okay, which is actually my Si minus A inverse. This is actually equal to 1 upon S plus 1. 0, 1 upon 3 s minus 2 minus 1 upon 3 of s plus 1 upon 1 upon s minus 2. So this is my phi of s. So then we will taking the inverse Laplace transform, we get phi of t is equal to e to power a t, which is equal to e raised to minus t 0, e raised to power 2t upon 3 minus e raised to power minus t upon 3, and here it is e to the power 2t. Okay, so this is the expression of phi of t. Okay, so this has been found. Now what is phi of capital T? Phi of capital T is equal to e to the power a into capital T. That is equal to e to the power minus capital T 0, then e to the power 2t upon 3 minus e to the power minus t upon 3, and here is e to the power, sorry, e to the power 2 capital T upon 3 minus e to the power minus t upon 3, and here it is e to the power 2 capital T. Okay, so this is the expression which we have got for phi of t. Now what do we need? We need what is known as gamma. That is integral of 0 to t into power a t into b into d tau, right? So my gamma is equal to integral from 0 to t into power a tau b into d tau. So that is 0 to t into power a tau is what? E raised to minus tau 0, e raised to 2 tau upon 3 minus e to the power minus tau upon 3 and e to the power 2 tau. And what is b? B is 0, 1. 0, 1 into d tau. So gamma is actually 0 to power t, e to power minus tau into 0 is 0 and 0 to 1 is 0. So this is 0, right? This into 0 is 0. This becomes e to power 2 tau into d tau. So when we integrate, this becomes equal to 0 and this becomes equal to e to the power 2 tau upon 2, and the limits are from 0 to t. Okay, so this becomes equal to 0 e to the power 2t minus 1 upon 2. This is the gamma. So this is the formula for gamma, and our phi of t we have already obtained. So now, how do we proceed now? Like we have found all these. What we will assume? We will assume our t is equal to 1 second. Let us assume t is 1 second. So what do we get? Our phi is equal to, what is our phi? E to the power minus 1, 0. E to the power 2 upon 3 minus e to the power minus 1 upon 3. And here it is e to the power 2. Okay, let me get my calculator. Okay. So that is e to the power of minus 1. So that turns out to be equal to 0.3678. This is 0. Then e squared minus e raised to minus 1. It is 7.021176 divided by 3. So that becomes 2.340. Okay. And e raised to 2 is 7.389. This is 7.389. Okay, so this is the phi matrix which we got. Phi matrix. And what is the gamma matrix? So that is 0, e to the power 2 minus 1, N square minus 1 upon 2. So that becomes equal to 3.1945. 3.1945. So now we can write what we can write. We write out x k plus 1 tau is equal to 5 into x of kt plus gamma into u of kt. So we must remember that the input is a discrete value. So it is the output of a zero order whole. Okay. And what is our y of kt? Is equal to c into x of kt. Okay, so these are the values. So this is what Sir has done. Now, Sir has considered another case where my input is sampled at a rate of 1 upon t1 per second and the output is sampled at a rate of 1 upon t2 per second. So what is shown that with different sampling rates for input and output, we can place the poles as we want. Okay. So what we just have to do is we are sampling the input at some rate. We are providing a sampled input or a discrete input to our continuous time system at one rate, and we are sampling the output of our system at another rate, at T2 rate, okay, at a rate of 1 over T2. So what Sir has considered again, they have a sampler with sample peak rate T naught and a zero order hold to each input. So the input in this case is a discrete value. And how does this state change based on this discrete value has been derived over here. Okay, this is how it is derived for that interval of time. And then the plant outputs are sampled, right? And the values are given. Then what is the final expression is this C times xk plus 1 t naught is a function of k t naught minus gamma into u of k t naught, right? Where C is a n bar cross n matrix and gamma is a n cross n matrix and y is a n bar vector. Okay, by what is n bar? It is n1 plus n2 plus dot plus np, a summation of I equal to 1 to p n I. Okay, summation of I equal to 1 to p n I. Okay. So y of kt0 is a stack of multi-rate sampled outputs during this interval. Okay, it has n I samples of yi taking uniformly at kt plus delta I very so much. Okay, so this is the input u of kt naught and this is the final state x of k plus 1 t naught. So these are the expressions. So here actually Sir has shown only one input, which is something. So it's actually there are M inputs and P outputs. So it is more complicated, but let us see for a very simple system. Let us consider a very simple system and we'll try to understand what is actually happening to our system. Okay. So this is the expression which sir has got for x k to the power plus tau. He has got an expression. This expression is using for the output yi at sampling extent L delta I. Okay, so this expression is getting in terms of x k plus 1 t naught. Okay. What we will consider is we will consider sum, where we will be considering this, where we will consider these expressions and we will be trying to solve it. Okay. So let us consider the system. This is our space system. We'll see. So we have our A. A is equal to 1, 2, then 3, 1. And what is our B? B is equal to 3, 1, 3, 1. And what is our C? Is 1, 2, 0, 1. So our C in this case is 1, 2, 0, 1. So actually it is kind of like a C1 and a C2. Okay, so this is our C matrix. Now let us consider, we have to first check if the system is observable. That is our first criteria. So we will first start observability. We'll do an observability test. Right? Simple C transpose and C transpose A transpose. So what is C transpose? Sorry, we C into A. 1, 2, 0, 1 into A. 1, 2, 3, 1. So this is 1, 2, 3, 6, so 7. Then 1, 2, 1 into 2, 2, plus 2 into 1, 2, so it is 4. 0 into 1, 0. 1 into 3 is 3. 0 into 2, 0. 1 into 1 is 1. Okay, so this is our CA. So our observability matrix is what? It is CA. That comes out to be of the form 1, 2, 0, 1, 7, 4, 3, 1. Okay. So what is the rank for this? This rank will be 2. We will check. This is our session. Let us add our A matrix. A matrix is 1, 2, 3, 1. 1, 2, 3, 1. B matrix is given by B matrix given by 3, 1, 3, 1. C matrix is given by 1, 2, 0, 1, 2, 0, 1. Okay, let us run it. C, I think from C into A. This is our C into A. So our observing matrix is equal to C and C into A. So this is the matrix if you get. Let us find the rank of it. It comes out to be 2. So this rank has to be 2. Okay, it has to be 2. This can only be 1 if this entire row is 0, which is not happening. That is why this rank is 3. And the rank is 2. Next, we want to find what is the rank of A, B, C, 0. We need to construct this matrix. We need to construct this matrix. That is A, B, C, and 0. Okay, so what is our A matrix? A matrix is 1, 2, 3, 1, and the B matrix is 3, 1. Our C matrix is 1, 2, 0, 1, and hence this will according to be 0, 0. Okay, so this is what n rows plus p columns, right? Into n rows plus into n plus m columns. So these n plus p rows and n plus m columns. Okay, so here I have this given over here. Okay, so that means if you will observe, this is the matrix which we got. What is the rank? So if you want to find the rank, so this actually is 4 cross 3. So the rank, maximum rank possible is the minimum of the number of rows cross number of columns. Any of them. Okay, so it can be maximum rank can be equal to 3. The maximum rank can be equal to 3. So now, if it is 3, what we have to do is we have to find this determinant. This determinant. So let us find the determinant, that is determinant of 1, 2, 3, 3, 1, 1, 1, 2, 0. What is this determinant? 1 into minus 2, minus 2 into minus 1, plus 3 into 6 minus 1. So that's equal to minus 2 plus 2 plus 3 into 5. That is equal to 15. Hence, the rank is equal to 3. Okay, the rank is equal to 3. Now let us consider this condition. We have to find the observability index by checking this. N1 is greater than UI, N2 is greater than N2. Okay, we have to find the observability index of this. How much can we observe? So let us do that. We have what is given by AB00. Let's go to the next page. We have to find AB00. This is what is our A? So A is 1, 2, 3, 1. 1, 2, 3, 1, 3, 1, 0, 0, 0. Okay. And what is C0? So what is our C0? So we have a C1 0 and we have a C2 0. Let us consider first case. So we have 1, 2, 3, 3, 1, 1, 0, 0, 0. This with C1 0. What is our C1? C1 is 1, 2, 1, 2, 0. Okay, we have to find the observability index of this. So this will be considered like our A new, and this is our C new. Okay, so let us code it out so that it can do our calculation, because this becomes a 3 cross 3 matrix and their calculation becomes quite a bit computationally intensive. Although it is not impossible, it will take some time. So we will do this also we have found out what is the rank. Now what we will say what is our A mu. That is equal to A and B 0 0 0. This is our A mu 1 2 3 3 1 1. This is our C1 mu is equal to C matrix, the C matrix, and its first row and all columns, and then 0. C2 mu is again the C matrix, but its second row, all columns, and again 0. So this is A mu, C1 mu, C2 mu. Now we have to find the observability. What we do, we do C1 mu, come on, C, this C1 mu, T1 is C1 mu cross A mu C1 mu, C1 mu into A mu, and then C1 mu into A mu into A mu. Okay, let us check this. What is the matrix which comes out? This is the matrix which is computed, and if we will find the rank of this matrix, it comes out to be 3. Okay, so it comes out to be 3. Next, we will look for the observability matrix for the second case. That is C2 mu, C2 mu into A mu, C2 mu into A mu into A mu. Okay, this comes out with third observability matrix, second observability matrix, and we do the rank of this. It comes out to be 3. This comes to be 3. So, what is the observability index? For both outputs is 3. So, we are determining that the observability index for both outputs is 3. That means my output 1 also has to be sampled at least 3 times, and output 2 also has to be sampled at least 3 times. It can be sampled more times as well. We can sample it for more times. There is no one stopping you. But this is the minimum number of samples you have to take. So then you may say that, okay, then let us take as many samples as we want. But then what will happen is the computation will become difficult. We will have to have very high power ADC, and we have to take so many samples and we have to store that data. So it is not always feasible. So we have found that the minimum number of samples we need to take is 3, both the output 1 and output 2. And remember, our input, which is being applied to our system, is a discrete input. It is the input being provided from the output of a 0 or a 4. Okay. So here we have shown that sample data control can be implemented for a consistent system, and the multiple rate output controller project promising option. And we don't need an observer. We don't need a dynamical system for an observer. Okay. And now we will see more details into MROC in this next lecture. Right? So what you have to take away is using multi-rate output control. What we are getting is we are getting the expression of the output. This is the expression of our output of the state, the next state. That depends on the various samples. These are the various samples of each output at different time instance. Next output at different time instance. Third output at different time instance. And this gamma of u of k t0. Okay, these have to be computed. So what I want to show you is this C1, this, all of these are going to be constant. They're not going to change. Even these are going to be constants, right? So let us go over this computation. So what we are seeing is what we are observing. We are getting a new. I like to do a C bar to remove confusion with the old C. I want to name it as C bar. So C bar of x k plus 1 t0. This t0 is the output, is the sampling period for the input. C bar of x k t0, this is equal to gamma y of k t0, this y vector of k t0 minus gamma of u k t0. So u is a discretized version of the input using a zero order hold. So there's a zero order hold at the input that is flowing to your system. And y bar is a row, is a vector of the output, of the sampled output. Okay. So let us consider in our case, we have n1 should be equal to 3 and n2 should be equal to 3. This is the minimum. And this minus gamma u of k t. So let us find what is our C matrix and everything. So you will go to MROC and go over there, implementation, matrices. We have to find. Okay. First is we will take n1 to be equal to 3 and n2 in this case we will take it to be equal to 3. Let us assume. We could take n2 is equal to 4 also, right? Our t, what should I keep it? A to n1 del 1, del 2. What is our del? Del is t naught upon 1, right? Okay. We assume t naught sampling period for the input of 1 second. So we have t naught is equal to 1. Okay, my del 1 is equal to t naught by n1. My del 2 is equal to t naught by n. Okay, this is my del 1, del 4. I got my del 1, del 2, right? Now let us try to find out this C matrix. We already found out this C1. Let's remove the C1 new. So for C matrix, this C matrix is given by C block 2. So this is C column C. First row and all columns C into EXPN of minus of A into N1 into del underscore 1. Okay. So let us get this is C mat, first one. Then it will be followed by this N1 minus 1 into del 1 and then N1 minus 2. Then this one, it is a C matrix. If you got an initial C matrix, if you have got, but we are not considered for output P. There should be a way to automate it. Yes. We have N1, we have N2. Let us say what's about P. So in the system, N states, M inputs, M inputs, and P outputs are there. Now in our case, we have N be equal to 2, M is 1, and P is equal to 4. So let us first find it. Let us first confirm it. Okay? So what do we have? N is equal to the sine of A. So N sine of A. The first one. We say first one. Okay? So this is the number of states in a system. N is equal to size of B in terms of the number of columns. That is what N equal to be 1. Okay. So this is the number of inputs. And our P is equal to size of C. C in the terms of number of rows. So C1. That is on it. So this is the number of outputs. So these are the number of outputs which we have as our system. Okay. So now we have N, N, and P. Now we have to find the C matrix. So we have N1, we have N2. So I will go from 1 to 2. Okay. Then for J going 1, 2, and 1. Let us say uh, 2 and 2 also going to P. J will go from 1 to N1. This is the first case. And the next case, J will go from 1 to N1. Okay, let us consider first case. I equal to 1 to P. These go to 1 to P. So, what about C matrix? Is equal to initial C matrix will be equal to zeros instead of one row was P outputs, right? So it is 1 comma P. So this is 0. Now, what do we do to it? So we will do C matrix. It's a predefined C matrix and C by row all its columns PXPN over minus A into any one to build underscore one. Okay, the next space it will be A into two. It will be N1 minus 1 and next here it will be N1 minus 3. Okay. So how would we code that? J is going from 1 to N1, right? So this would be N plus P minus J. Let's check this. So what is the overall C matrix? 1, 2, 3. So once it can with this, a little bit out, a little bit over. So first, minus 3.003, let us check with this. What is coming? Okay, this is coming. So this is for the first set of inputs. Now this has to be changed to N2. And when it goes to P, it is the next set, right? So that's P, 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 minus minus C matrix will be given. Then we follow N2, right? And then C matrix. The C matrix is coming out with this. Okay. Next we are equals to 1 to 3 goes to 1 to 2. This is the end of 2, right? And here J equal to 1 to, let us get this end of 2. Let us on this. This is the C matrix. Go to the C what's coming is out for this will be entire. This is C matrix which is computed. So these three rows are first, these are first. Now the issues we have this C matrix. So C matrix in this case, the C matrix would be from T to N. You want to get it on the first and all the numbers. So these are the new C matrix. So this is the new C matrix. Okay, so this is just for adding generating initial structure. And then we have used the loop to calculate what is the overall C matrix. into the row container zero. Which are not needed, which are not needed. So these are C matrices again. Now, next is what? So we have found the C matrix. So now we have to find gamma. We have to find gamma, we have to find Y. Y we will find based on the samplers. That's 18 or older, but we have to find gamma. So gamma can be determined. Gamma can be determined. Mhm. Gamma C1 into this, the integration we need to do. We need to do an integration which goes from 0 to minus n1 delta 1 into e to the power 80 b into dt. Has to be done. So the inputs are just the input is remaining the same. E to the power 80 into b remains the same. Only the C1, the limits of integration is changing. Only the limits are changing. Then it is getting multiplied by something else. So how do we do that? So it is e to the power 80 into b into dt. Okay. Let's say since was we have our expression of EXPL A into P. Okay. With our expression EXPR. It is some expression A into T. This should be into B. What is like this further? So it comes out to be like this. This is our expression. This we have to integrate this expression. Okay. From 0 to C of B to B. This is integrating from 0 with respect to T from 0 to, let us say in the first case, minus n1 del. Minus of n1 into del into 1. Let us run this expression. It comes out to be like this. So this is here. We can get a better way. We can get a numerical format. Comma 4 comes out like this. So this is our first thing of gap. So this has to be multiplied with C1 for it. This will be multiplied by P the first row of 1. This is a numeric value. Okay. So this is one number which we get. Similarly, we have to get for multiple numbers. So let us go with this thing. The next is this. is 4 minus n1 into del 1 is minus n1 minus 1. Minus n1 minus 1 into del 1. Next case is minus n1 minus 2 into del 1. We'll run this section. This is the gamma we get, right? Here we go. Once we get this gamma, what we do for it? We can get it for the further matrices, and let us check whether there's any way to get it in a simpler way. We'll put the iterative solution for this. After gamma is right. So we will find the quantity n from gamma is equal to gamma. And then u of y comma 1, so then this BPA into BPA of integral BPA will project of integral of this expression for integral which we have to do. So this thing should be del 1, del 2. So del equal to del 1 del 2. It should be del into j into I. So integral of expression, what is the expression? That will be integral of expression from p 0 n of I plus 1 minus j into del of I. Let us run this one to one. This one So what is this expression given? It is the comment. This is the let's try this method. Demo JS come. So what happens? Comes out to be like this. Demo. So, there's no problem over here. So we can write demo. Equal to this. And this. And right now, we get whatever demo. Comes out to be like this. Then to equal 1, 2, 3. And we get this. Then we say gamma rename everything. We do gamma is equal to EPA gamma from 2 to N command 3. We don't want it to be very long. So we'll run this section. This is our gamma which we get. This is our gamma which we get. So we got our gamma. So we got a C matrix, we got our gamma matrix. These are again constant. And y is a n bar vector which comes from our samples of our output, which we need the samples from output. So when we get that, we get the input to output state matrix. So this is the expression which relates the y to the input as well as to the final state. Right? So here y is related with your inputs, which is this, as well as the final state with this. So why don't we try to find the rank of C and tau? C and gamma. So the rank of, so what is our C matrix? This is our C matrix. Okay, 1, 2, 3, 4, 5, 6. Let us do size C matrix. Size and gamma. So let us run it. C matrix is 7, 2 and gamma is 7. So 7 goes to column, 7 goes on column. Now we have to find C and gamma. So, C now and gamma. Let us find what is this matrix? It's got like this. Okay, we will write this matrix. Let us find the size of this matrix. MAT. It is 7 to 3 column. That comes to be rank 3. So this round comes out to be 3. It will be n plus n. N is the number of inputs, P is the number of outputs. So comes to be equal to n plus. Okay, so what we have shown is instead of going through all this pain I have to go through to find out whether it can be controlled, very multi-rate output controller. Instead, what we can do is we can find out whether the system is observable, right? Then we can find a round of this kind of matrices which are easier and smaller to compute. And we can also get some, we will find the observability index for both these inputs, both these outputs. Okay, and you have to just find a rank of this matrix. If we do all this, this is a test for this overall big test. So without computing this large C matrix and this large gamma matrix, I can use these tests which are equivalent to this test to prove that it will work. My multi-rate output controller will work. So now let us go to the next lecture. We have found the C matrix, gamma matrix. These are the expressions for them. And this is what we found. Now they're saying is we want some output. We want some controller. And this controller is dependent on the samples of the output which I have. Okay, we have to design some M and L respectively. So first case is M should be stable. M has to be stable. If M is not stable, then our it will not work properly. It will not. It has to be stable. And this is our U is given as a function of the state. We have a state feedback control law. So effectively, we will get the MROC law to be given by this expression. And for this expression, what we will require, XC should be equal to F and M should be L into gamma. Okay. So let us consider this expression again. What do they mean? So we have seen it has been derived by Sir that is C bar x of k plus 1 into T0 is equal to your is actually equal to y of kt0 y bar kt0 minus gamma of u kt0. So these are constant matrices and these are also this is like a constant vector or a constant matrix depending on the dimensions, depending on the number of inputs. And these are the samples of the various outputs. Okay, these are the samples of the various outputs which we have. So now how do we deal with this? So this is the way our input, output, and states are related by this matrix for this sample data control system. So now let us see. We want to do what is the state feedback. We want to do state feedback. So what is done is if UKT0 is considered as state multi-rate output control. Earlier we were seeing what is the equations governing the system when there is a multi-rate for sampling the output as well as sampling the input. Now we will see how do we design a controller which will give us this input. So the k plus 1 t naught input, which is this from coming from the zero order rule, this should be given by this expression m minus this certain design L, which we are using for design, into the samples of my output. Okay, so the U which I require for my next control, next input, next instant is given by m into my previous u minus L into the samples of my output. Okay, these are all the certain samples which I've taken of the various outputs which we have mentioned, right? So we have to get this. Now, what is considered is we will try to find an equivalent state feedback law. Basically, we have seen what is state feedback. We have seen it for continuous time systems, and we have seen that state feedback has a lot of advantages. We can do pole placement, we can place the poles, and there are various mathematical tools available when we consider state feedback. So we want to again relate that concept of state feedback. So what they do is they consider law. They consider state feedback law u of kt is equal, which is given by minus f into x of kt is. Okay. So let us substitute that. So that's saying u of kt is equal is minus f into x of kt is equal. Okay, this is minus f. Now u k plus 1 t0 is m into u k t0 minus l into y k t0 is the old one. Okay, now they are saying that if LC is equal to F and M is equal to L into gamma, then we can realize the state feedback again. So what they want is they are pre-multiplying the state transition, the state equations by L. Okay, they are pre-multiplying it by L and they are finding this expression. Okay, so let us just check this expression again. So what we have seen, this is our expression. What they do, they will, what they do is pre-multiply by L. So what we get LC is LC x bar x of k plus 1 is 0 is equal to L into y bar of k t0 minus L into gamma mu of k t0. So this is what we have got. Now we want L of y bar k t0 is equal to this LC bar x of k plus 1 t0 minus plus L into gamma u of k t0. Okay. So what we do is we will substitute this over here. We substitute this over here. So what we will get u of k plus 1 t0 is equal to m into u of k t0 minus of LC x k plus 1 t0 plus L gamma u of k t0. So we get u of k plus 1 t0 is equal to m minus L gamma. This actually is gamma. Gamma u of k t0 minus LC x k plus 1 t0. Okay, so that is this expression. Okay, so it is like kind of like state feedback. Okay, what do we get is m minus L gamma is equal to 0. If we can prove this m minus L gamma is equal to 0, and this LC label as that, then we are kind of getting the kind of state feedback control law. So what they want is basically what we want u equal to minus kx, right? Or u is equal to minus fx. So you don't want this. You will set this to 0. And this is set as f. So what they are doing is maybe m minus L gamma should be equal to 0. This LC should be equal to 0. So that is the objective which is done. That is what this derivation says. So they found. So another criteria which we must remember is all poles of M should lie within the unit circle. If that happens, then only this equation, where is this equation? Then only this equation will be stable. This equation is stable only if M, all the poles of this M matrix lie within the unit circle. Okay, because we are considering a discrete time system, a discrete system, right? So this was considered, M was found. Okay, they have told M should be within the unit circles, otherwise a different F should be selected. So iteratively, they will find F. So first they will choose one F, you will get an L, then L they will use to find the value of M, because gamma also we have already found out, and then they will decide whether the properties of the system are good enough, or we have to again reiterate and we have to again modify F. Okay, so it's just an iterative process. Okay. So one case is when this number of samples is equal to the observability index, when each output is sampled at the value of the observability index. But in certain cases, we may want to take more samples. So when we take more samples, what will happen is we will have less equations, but we will have many unknowns. So in that case, there can be multiple values of L, and then they can choose any of those L values to find the stability of L. Okay, so you have more flexibility in that case, right? So this was shown, and sir has proved. This is our UK plus 1 T0. This is MUK T0. So this is what sir has combined. So this is the equation sir has merged. Okay. So what has sir done then? Fine. Thank you. Let us check this. So we have u of k plus 1 T0 is equal to m into u of k T0, right? Minus L into y bar of k T0. This is how you find the u. Your u input is formed like this. Next is we have LC of x bar, or x is just x, k plus 1 T0 is equal to your L, this is L, into y is again repeated over here. Okay. It is L into y k T0 minus L gamma mu of k T0. Okay, so these are the expressions. So then they found your LC should be equal to F and M equal to L gamma is required. M should be equal to L gamma. Now, what they find, u of k plus 1 T0 is, okay. So they write u of k plus 1 T0. What is M? It is L gamma mu of k T0 minus L into y. It is minus LC x minus L gamma. Okay. So that is we are substituting the value of Ly. L by k T0 is what? LC into x k plus 1 T0 minus L gamma. So here you have this Ly. Means just take it to the right hand side. So this becomes minus LC x k plus 1 T0 plus L gamma U of K T0. Okay, that becomes equal to minus this minus same this minus LC X K plus 1 T0, which is equal to the minus F X of K plus 1 T0. Okay, this is again just reiterated. So now what do we get? U of K plus 1 T0 is minus F into phi naught. So let us see what is this phi naught as. So X K plus 1 T0, what have they defined phi naught to be? Phi naught gamma naught minus F into phi naught minus F into gamma naught. Mhm. Check this. Using the transformation of state variables, we get in this form. Okay. So now they have done certain analysis. They have seen that for a closed loop system with MROC, there are n poles with the state feedback and n poles which are located at the origin of the cell. So there's certain constraint. You're placing poles, n poles you can place with state feedback, but there are n poles which are located at the origin of the Z, for which you don't have any control. Okay. So we just find out matrix is e to the power 8 2. Okay, gamma naught is given by that. State feedback gain is here. They get 5 matrix, gamma matrix, C gamma by. Okay, they get this is an example which Sir has shown. When they found the C matrix, then they found L, and they further found gamma. They have what they have done is they have considered certain state feedback gains they have considered. So that they place the eigenvalues at this location. Okay. Hmm. Let us check for our system, which we have considered. What C matrix, gamma matrix we have got. Right. Let us consider pole placement. So what do we have? For 80 and 40, so we have phi naught and gamma. In that we place the poles. We have to compute phi naught. So phi naught is EXPM A into P naught. P naught. Okay, this is phi naught. We will get phi naught. Then gamma naught is given by our integral. This is our expression. Integral of expression t equal to 0 t naught. Okay, this is the integral of that. So what is gamma naught? Comes like this. We want it to be numeric. So we do VPA of 3. Let's see what it comes to. So this is our gamma. So we got our phi naught, we got our gamma naught. Now we have to place our poles. Let us say poles. We will place it at minus 0.1 and 0.1. Okay, let's just take this. Okay. Now the F is place of phi naught, comma, gamma. This is our F. Okay, not poles. So this one. Gamma naught matrix when we convert it to W. If because it was symbolic two works were variable it wasn't used, so we converted W. So we got a F matrix we found. So this is our gain matrix. This is like our state feedback. And this is our state feedback. Then we got the phi, we got gamma, we have a C matrix. What is our C matrix? What is this is our C matrix, right? This is our huge C matrix. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. 7. So our L is F into C inverse. How do we get C inverse? Just try. Just matrix inverse. This is suppose in this case, C1 was what? 3 was C1. Then 7 1. Notice C1 is 1 row, 3 columns. 1 row, 3 columns into E1. Okay, that will come out with 1 row, 3 columns. 3 plus 3 is 1 row, 3 columns. So 1 row, 3 columns, 1 row, 3 columns, 3. Right? 3. Now it is C matrix is why not is it is not coming. C matrix is N1 into power minus A, N1 into delta 1. N1 into delta 1. In our case, this will be 1 row, 3 columns. In our case, it will be 1 row, 2 columns, 2 row, 2 columns. This first row of it. First row of this will be 1 row into 2 columns. The next row will be 2 row, will again be 1 row into 2 columns. With that, we are getting a C bar matrix to be 7 plus 2 because it is N bar. It's N1 plus N. This 2 is N. C bar equal to N bar plus N. So in our case, it is not in. To be done in that case. This we are seeing our multi-level output controller that is very fast. So we have considered multi-level output controller means what? My input is sampled at 1 rate, 1.0. But the output is sampled at 1.0, 2.0, and then 2.0. Multiple rates are there for output. But output is sampled much faster than that. So this the observability indexes for each output is different, and the number of times that output is sampled also is different. What that is maybe generalized case. When all output is sampled at the same rate, use N1, N2, N3 sample every time. And they have shown that this controller is non-dynamic. It is a non-dynamic. Okay, so this is the output is sampled at 1 rate. All the outputs in this control signal is generated according to U of t is equal to y of t. So in the previous case, if you would have given one, what we have shown is my input is generated is dependent on the previous input as well as dependent on the samples of my input. In this case, it is just dependent on your y of t. L is also this. And this is the while KP. And let's see lecture 27. The y1 of KP0 to n1 minus 1 into that one. Y2 of KP0 to n into minus 1 delta. So it will depend on the current sample. So depending on the previous sample of the R. But in this case, it depends on the current input as well. Current output as well, which is kind of I think is bit problematic. So we find out what first state feedback giving. So the closed loop system is stable. Okay. But then there should be no code methodology. That has to be made sure. You have to select such a name. Okay. There's a L license state feedback and the execute where C is given by this expression. And this is the expression for C naught. This is the expression for D. This was divided over here. And this is the closed loop system. State feedback gain is 1 minus. Okay, so L can be obtained if C inverse exists. And for this, they have to show that the number of times the output is sampled should be greater than the observability index. And they have selected F such that there's no pole at the origin. Okay, this was shown. So this is for fast output sampling. Next, let us consider another case. We'll consider class of sampling data control system, which is a sampling rate for inputs and for outputs is different. Okay. Previous two ways, multi-rate output controller and fast output sampling controller. The controller is there which in one input sampling interval, output is sampled 7 times. But in now what we do, the sampling rate for different outputs. Now what we will do is the outputs are sampled at the same rate. And the inputs are sampled at several uniformly spaced instance of time during one output sampling period. Okay, and the control gain is periodically varying. So what happens with the POF controller is the input depends on the previous output. Okay, and the gains which it is using changes periodically. So when these gains are changing periodically, what happens is the control input is discrete. So the control input is no longer like a zero order mode over the sampling period. The control input is changing. Okay, depending on the input sampling. Okay, so it is shown that this POF controller can also achieve arbitrary pole placement, which it can achieve. So let us see this. This is the discrete-time system which we found, and there's a sampling at a different rate, right? And certain control gains are assumed to be periodically varying. So the input is updated n times for each output sample. So output sample is fixed once, then our input is being changed. So there's a design. So if you will see, this is my output that's been sampled once. Then at 0th instant, you use K0 set of gains. Next instant, it will use K1 set of gains. Next instant, it will use K2 set of gains. And again, it will use K of n minus 1 set of gains. Okay, so this is the input. And again, the input is also not fixed. Okay, input also is like based on a zero order whole. At the sampling interval of delta. So these are again the expressions, the whole computations which are done. This is the input that is generated. The input is periodically varying with time. That's why it is periodic output feedback control. And the gains are changed continuously. Okay, so this is the equation. The gain G is designed so that the poles of the system are lie within the unit circle. And then they confine gamma into K is G. And this is gamma. Okay, gamma will have full rank if n is bigger than u. So here, in this case, it depends on the controllability index. But in the previous case, it depended on the observability index. In MROC and FOS, it depended on the observability index. In our case now, it depends on the controllability index, the system. Okay. So here gamma k should be equal to G. So here what is required is the sample system should be controllable and observable. The number of subintervals in T should be selected satisfying n should be greater than equal to mu. If n is pure, solution of gamma would be unique. If n is not, If n is greater than u, then there will be several solutions. If n is less than u, then we cannot get pole placement. We cannot just periodic output by complete. We have to increase our sampling rate. Okay, so this is the one which are considered, and there are various examples which are shown. Okay, so observer is not required. In this case, also observer is not required. And output injection gain can be less in poles to the sampling data system for the sample period T can be placed as desired. So these poles are with respect to the sampling period T. This is not the sample period T. It is not for the T by N. It is for the overall response of the system, which you look at it for the sampling period T. Okay. So we have looked at MROC, which is multi-rate output control. Next, we have considered FOS, which is fast output sampling. Next, we have considered POF, that is periodic output feedback. Okay, so these cases depends on observability. This depends on both controllability and observability. Okay, here it is the controllability index. Here it depends on the observability index. Alright. So they say so MROC is a bit advanced and computationally intensive. FOS, it is a subset of MROC, but there are certain constraints. There should not be any pole at the origin. While in MROC, you get a certain set of poles which lie at the origin. In POF, you have, what is known as a discrete or discontinuous. Then discrete or discontinuous inputs. When you have these discrete and discontinuous inputs, it may not always be acceptable in every system, but in certain systems it can be acceptable. And in such cases, we will rely on the POF controller. Okay, so very week 9, we consider digital control. So this is a recap of this session. Consider it for the case of sample data system, where you sample the input, where you sample the output. And first case is a generalized case, where you sample the input at the same rate, you sample the output at the same rate. And that was a very nice thing. But they have seen, people have done research and shown that if you sample the output at multiple number of times, more number of times as compared to the input, then you get certain properties, you get certain flexibility you will get. Also, how many times should I sample? So there should be a minimum number of samples required. And if you get, that is not found by the observability index, and if you get that certain minimum number of samples, then you can do pole placement, arbitrary pole placement you can do. So you don't need, in that case, you don't need an observer, you don't need to estimate all the states. You can get a control law, which is equivalent to state feedback without actually measuring all the states. You're just sampling the output multiple times. Just sampling the output multiple times and you're getting such good properties. Okay? So the maths is quite complicated and we are considering uniform sampling at a fixed rate, right? So you have an integrator, you have differential equation, discrete time systems, we have delay, And discrete-time system, we use what is known as difference equations. The condition for stability for discrete-time system is different. Poles should lie in the left half of the plane. For a discrete-time system, poles should lie within the unit circle. So that's why I was confused when the was written that the poles should be placed at 0.52 plus j point 1 plus or minus j point 1. I was confused. Why? How can you do that? Because the poles have a positive real part, but then what is the thing in discrete-time systems? The pole should lie within the units. That is important. Right? Then we consider what is sampling, what is uniform sampling is shown, how an ABC is required in an actual practical system. Okay, when you have a number, then you convert it to a digital value. And this is the common bits. So, certain number of bits. That you will actually start to try to practically implement the mapping system. So this is for fun. And we have to understand something that when we are doing this analysis, we are considering that the input to my system is actually discrete. There's no longer continuous. It's coming from a zero output. Right? So we consider one sample of input and output at a certain date. In find how do you find the state transition matrix? Earlier, when it was it just had to be done by the computer. I thought. But then I realized that it's just like the state transition matrix. And you can find the state transition matrix using Laplace transform. It is the way which I prefer. Okay. So we found the state transition matrix. Then we have to use partial fractions method. And then we took the inverse. We got this expression. Similarly, how do we find gamma? We have already found e to the power p. We just substitute by tau, and multiply by p, and then we just integrate each and every term inside this expression. Thus we found gamma is found. Then we substitute value at we consider a sampling rate of t equal to 1. Then we will get this expression. We consider a different rate of sampling, then the expression will change accordingly. Right? So this is the case when we considered a fixed rate of sampling for both the input and output. And then we did also this for MROC control. We found observability test we did. And then this giant matrix also we found the observability. Okay, then we found the observability rank, the observability index for each and every output because there are two outputs in this case. And then we went through search, derivation, or return or receive, what are the various things which are there. And we also did certain mathematics, certain code was done. We tried to make it iterative with group-wise flashing to make it simpler and easy. And we also consider what if we do state feedback, we will decide certain pole locations and how do we find the gains which are required for the state feedback. Equivalent state feedback control. Okay, so thank you, and I'll end this session.